Hay que mantener ese HDMI para que se pueda cargar. ¿Cómo? ¿Eso puede ser un HDMI? Sí. Ya, está creo que una segunda parte. No. ¿Funciona? No, porque en realidad no está conectado. ¿Dónde está
Porque está de adorno, parece.
funciona el técnico?
¿No? Según eso.
Sí, porque no. Para hablar.
¿Está café?
Sí. No sé qué van a quitar.
¿Y improvisaste si es portero? Hace rato que no pienso. No tiene pila. No sé si se va a ir a los adaptadores en realidad.
No se está compartiendo la pantalla.
Quizás está compartiéndose otra pantalla. Porque creo que está en mi.
Creo que era así. Sí, súper. Perfecto.
Y te voy a decir si puedes poner grabar.
Creo que aquí le gustaba.
¿Lo pusiste a grabar cómo? Está bien.
Sí.
Buenas tardes a todos y a todas. Bienvenidos a un nuevo seminario de grado C. Hoy tenemos el agrado de presentarles a Miguel Bezares de la Universidad de Nottingham, que nos va a hablar sobre Numerical Relativity meets Modified Gravity. Un aplauso para él.
Sí, hablo español, soy chileno también. La pregunta es, ¿quieren la charla en español o en inglés? Spanish. Ok, voy a poner el cronómetro. Entonces, hoy les quiero hablar de investigación, que es básicamente relatividad numérica, y en esta charla les voy a hablar sobre lo que es Modified Gravity. Primer disclaimer, no soy un experto en Modified Gravity, entonces si ustedes tienen una teoría que les gusta mucho, a mí también me gustan mucho algunas, y podemos compartir sobre todo me gustan las teorías. Pero les voy a tratar de explicar cómo la relatividad numérica puede ayudar para estudiar esta gravedad modificada. Entonces, las primeras slides que les voy a mostrar son acerca de mi motivación para estudiar esto, porque cuando yo empecé en esto no sabía nada. Me ofrecieron un proyecto de gravedad modificada y hacer simulaciones y no sabía nada, y creo que sigo sabiendo poquito. ¿Ok? Pero este es mi takeaway de la gravedad modificada. Entonces, uno puede encontrar que hay muchos argumentos para considerar extensiones o modificaciones a relatividad general. Sin embargo, relatividad general siempre es la más linda, pero uno puede considerar extensiones. Hay gente que trata de extender esto para responder qué pasa con Quantum Gravity, Dark Matter, gente que trata de responder qué pasa con Dark Energy, y creo que todos lo saben, pero estamos viviendo en esta era de la onda gravitacional, entonces podemos hacer test de relatividad general. Entonces, buscando la literatura para saber cuál es la mejor teoría o la que más le podía gustar a la gente, encontré este paper de Nico, un Living Review, que da como una lista de deseos de tu teoría alternativa. ¿Ok? Primero, tu teoría, la que te guste, tiene que estar bien fundamentada desde el punto de vista físico. Entonces, tiene que tratar de resolver un problema de la física, por ejemplo, cosmología, quantum gravity. Tu teoría debe pasar los precision tests. Después tengo que encontrar soluciones y esas soluciones no solo las tienes que encontrar, además tienes que probar estabilidad. Puede ser lineal o no lineal. Y algo que me gusta mucho, que es que tienes que ver si puedes formular esto en un well post initial value problem. Entonces, hay un zoológico de teoría alternativa. Una pregunta malintencionada. Por supuesto. La respuesta va a ser malintencionada.
No siempre sigue esta lista, también podría estar tirando a la basura las posibilidades de la física.
Sí, estoy de acuerdo. Pero me llamó la atención la lista y siempre trato de seguir alguna historia. Pero hay un zoológico de teoría alternativa. Yo no descarto ninguna. Hay gente que sí descarta, que tiene opiniones más fuertes. Se dividen, bueno, este bloque me gusta mucho porque puedes tener la massive gravity, puedes agregar un nuevo campo o puedes romper alguna assumption de relatividad general. Hoy día lo que les quiero mostrar es este sector aquí. Ojalá tenga tiempo de mostrarle todo qué se puede hacer con relatividad numérica y con Hornensky. ¿Han escuchado hablar de Hornensky? Yo sí, he hecho simulaciones, muchas simulaciones acá, aquí también, este es un lado muy oscuro, aquí más oscuro también, y muchas de estas de acá se parecen mucho a estas, entonces son casi equivalentes si les gusta hacer simulaciones ahí. Entonces, este es el paper de Hornensky de 1973, donde básicamente él propone the most general scalar tensor theory leading to the second order equation of motion. Y para alguien que hace simulaciones, si alguien dice second order equation of motion, es un target. ¿Ok? Le voy a explicar en un momento por qué. Entonces, Gregory dice que propone esta teoría para construir la teoría más general que pueda. Yo este paper no lo conocía cuando lo vi, entonces no entendía muy bien esto, pero quizá si ven el lagrangiano de esa forma, Hornensky es la suma de todos esos lagrangianos con diferentes funciones, muchas cosas no lineales por ahí y por allá. Siempre me gusta mostrar estas cosas sociales. El paper, hasta el 2008 más o menos, como que a la gente no le gustaba y después tuvo un boom, sobre todo a la gente de cosmología. Sí, sí, que ahora tiene un montón de citas. Entonces, hoy día les quiero mostrar dos teorías en las que he estado trabajando, Essence y Scalar Gauss-Bonnet Gravity, que vienen dadas por estas dos acciones. Entonces, mi charla va a ser de la siguiente forma. Les quiero explicar, voy a asumir que no voy a pelear con nadie, entonces voy a asumir que mi teoría es well motivated from fundamental physics. ¿Podemos estar de desacuerdo? Sí. ¿Ok? También voy a asumir que pasan precision test porque quiero mostrarles cómo funciona el screening. Pero hoy día el mensaje principal es que quiero tratar de discutir con ustedes estas tres preguntas que da de mi lista. Estas teorías admiten un initial value problem, les voy a explicar qué es lo que es eso, tienen soluciones y qué pasa con la estabilidad de estas soluciones en la parte no lineal, ¿ok? No en la parte lineal. Y sí, el main goal es, quiero estudiar la parte no lineal de todo esto, donde está toda la dinámica usando la herramienta relatividad numérica. Entonces, claro, ¿quién ha escuchado de relatividad numérica? ¿Sí? ¿Qué definición tienen de relatividad numérica? Acá.
Resolver las ecuaciones no lineales
¿Sí?
de Einstein enteras.
¿Sí? ¿Alguien más?
Bueno, escuchado, pero...
Entonces, por eso mismo, puse más slides hoy día sobre relatividad numérica. Puse 5 slides para poder explicarles. Entonces, el outline de mi talk hoy día, le voy a hablar de numerical relativity, scalar Gauss-Bonnet primero, Chi-essence, y después algunas conclusiones. Sí. Me cuesta mucho hablar en español, entonces voy a cambiar a inglés, ¿te parece? Yo estoy traduciendo lo que tengo escrito. Entonces, okay, so first, numerical relativity. There are classical books, Shapiro and Baumgarten, Miguel Alcubierre, a Mexican guy, and basically, yes, it's solving the Einstein equations numerically, okay? Then we have my definition here. I am very poetic, so I like to say that numerical relativity is the art of solving Einstein field equations with computers. Plus, I will show you nice videos. Okay. So the first question that I want to show you is how to take the Einstein equations and go to from the continuum, from this equation here, this beautiful equation here, which are a set of 10 nonlinear partial differential equations, to the numerics. Okay. So the recipe is the following. It is very standard. We haven't changed much for many years. This is like the kind of recipe of numerical relativity. So you take your covariant equations, you want to disentangle the time in the space explicitly, so you use the 3+1 decomposition. This is the metric here. Then you choose your gauge conditions, your equations for the labs and the shift. Then you combine all of these, and you have an evolution system. Okay, maybe some people are familiar with ADM formalisms. So you have, for example, equations for the metric, and for the intrinsic correlation. I will show you something later. And then, having your system of equations, you can discretize those equations and then let evolve, preserving the numerical methods and the well-posed. So if you see this work, and I have said many times, well-posed, is a red flag. Okay, I will show you why. So the breakdown of the numerical relativity problem, I really like these slides I took from David, is you take first, you choose your problem, your physical problem, okay? For example, you want to study core collapse supernova. I want to collide two black holes. I want to do black holes in some alternative theory of gravity. And then, okay, we choose our physical problem. Then we move to taking the Einstein equation in this case, or your theory, and try to write down an initial value problem, okay? And then in numerical relativity, it's quite important to study the well-posedness of the problem, which basically it means the unique solution, they exist, and continuous dependency of the initial data. After that, you can do free evolution or constrained evolutions, so that this is like the jargon of numerical relativity. You just take an initial data, you let evolve, this is the free evolution, and constraint is you solve the constraint and every time step. Usually people don't use this one because it's very expensive in 3+1 simulations, maybe 1+1 you can do it. However, this one is like the common one that everyone uses. Then you have your PDEs as a time evolution problem, you prove that they were well posed, and then you choose your numerical method. Indeed, when I want to study numerical relativity, I thought that people use like fantastic numerical method, the most sophisticated one ever, because they were evolving black holes, they were evolving stars. So I was like, okay. And then my code, for example, used finite difference, so which is a Taylor expansion, no, in the continuum. There are other codes, for example, who use pseudo-spectral method. For fluids, if you have fluid, you can have shocks. So you want high resolution of capture method. Then you want to call your code to be optimized and parallelized because you want to have a simulation in CPU maybe in 1 month, okay? So you need that everything to be super optimized, or you can use GPU nowadays and so try to make your code fast. This is one of the big things that you want to do. Make your code fast. And then I think this is the 90% of my research. So because usually this part is problematic, but here I spend all my life, which is basically extensive error testing. So you do numerical tests, you evolve known the space-time, you're trying to find all the bugs that you put in the code. then you take analytical solution. The analytical solution say it has to behave like a sign, and then you plot and you find a linear behavior. Then you cry, and then you try to fight again, and this is the most important one. And then convergence test. You increase resolution. You try to see that what you are getting, for example, is the same with more and more and more resolution because you are solving something in the discrete sector. So, for example, you can find as a friend who find a new black hole solution and evolution because he was using a very bad resolution, and he called me Miguel with a letter. Say, okay, fantastic. And then, so the resolution, it was very, very crap. And then we have, if you increase, everything will behave different at black hole, so nothing happened. So this is the most important one, 90% of the research. And finally, you start the physics and write your paper. So since we are in the ChatGPT era, I did my slide with ChatGPT. So this is my code. You can look in for on internet. We have a web page. It's open source. So it's called MHDoIt. It's an automatically generated code from another platform. And basically, yes, what I was saying, we have different numerical methods. We can model microphysics for neutron stars. We can model general relativistic MSD, modify gravity. I'm doing the heavy lifting of this part. Boson star, exotic compact object, whatever, black holes and neutron stars. It's a collaboration from the University of Balearic Island in Mallorca. My PhD advisor, this was like my kind of PhD. When I arrived, he was extending his own code to this new structure. And finally, we have the coding GPU. So now this is like a huge, for me at least, it's a very huge achievement because we can do binaries before in CPUs in a supercomputer using thousands of nodes and burning a lot of CO2. We were doing binaries in 1 month if you didn't do any mistake. Of course, never happened to me. And with GPU now, the code is faster and we can finish merger of black holes or neutron star in 2 days or 1 day if you don't do any mistake. So yeah, I promise that to you that I'm gonna have a video here, and I hope, yeah, of course you cannot see it over here. So what you are seeing here is a binary. So if you put all together, you can do this video. So this is a binary neutron star merger. This is the rest mass density, okay? And this is the quantity, the Neumann-Penrose scalar psi4, which contain the gravitational wave. And here you can see the gravitational wave. It's an unequal mass binary with a realistic equation of the state. And you will see as soon as they are approaching to the merger, the gravitational wave is going to increase. And you can see here, and you form that formula hypermassive neutron stars. So now I explain you what is numerical relativity in very, very few words. So what happened if I take everything that I say to you and I apply for modified gravity, or my favorite modified gravity, okay, especially this Kordensky. If you take all these elements and you do simulation of Kordensky, what you're gonna find is something like this. None, not a number. Your code will crash. Okay, and this was like the first year of my postdoc that nothing worked. And I thought that the problem was myself because I was putting many bugs. I usually put bugs in my code, but this is something that a PhD who was working with me at that time did this slide. I didn't really like it, but is due to the following: our new friend well-poserness. So mathematically speaking, have you heard about this property of PDEs? Anyone? Yeah. So well-poserness, if you have a time-dependent partial differential equations, you have here whatever operator derivatives. The formal definition, the Hadamard criteria say that your problem is going to be well-posed if you can find a solution, it exists, and then if you take that solution, you perturb it, it's not going to blow up. No, so it's going to be dependent continuously of the initial data. So solving this problem for your PD, for me at least, is quite mathematical. You need to solve the space, it's very complicated. But we have something called hyperbolicity. Okay, imagine that we consider that my equation I can written in this way, and this M here, this matrix here, contain all the higher order derivative. In this case, it's a first order reduction, but imagine that this one we call the principal symbol. Okay, so we will say that the system is strongly hyperbolic if you can diagonalize. Okay, you can really calculate all the eigenvalues of your matrix. And then we will say that it's really hyperbolic if the principal part has real eigenvalues, but an incomplete set of eigenvectors. So why is this linear algebra property so important? And this is a slide that I had for my first year of PhD that I never forget, that is why I really care about hyperbolicity. It's for this reason. If I show that my system of PD is strongly hyperbolic, I can prove, I'm not going to do it, but there is a theorem who says that your initial value problem is well posed. If my initial value is well posed, I can choose a stable numerical method and I can do stable numerical evolutions. Okay, this is like the last theorem. However, if you take a really hyperbolic formulation, okay, you take your equation and you find that you miss one eigenvalue. So the initial value can be imposed and then you will have an unstable numerical evolution. And this is what happened with general relativity. So people were doing simulation with the ADM formalisms, the triple one decomposition, and they didn't care about the hyperbolicity until the 90s, more or less. Okay, so here is a plot from this book that shows the following. So this is a constraint. Constraint in numeric means that something has to satisfy for all the time that you evolve. Okay, so the trace of the extrinsic curvature of this has to be 0 during your evolution. If you take a strong hyperbolic formalisms, we have some names, weird names, which is called the Z4, you will have, and you just evolve, this is called Rose stability test, you just evolve noise, white noise. Okay? Everything is stable. However, if you take the ADM in different forms, there is one eigenvalue, because it was really hyperbolic, people didn't realize about that grow and grow and grow, and shows that, for example, your code crash at some point. So this was the problem of the ADM formalism, which is not ADM, is not the ADM paper, is the York take the ADM paper and wrote down the triple one decomposition for these equations. So this is the lesson that we learned from numerical relativity in the 90s, 20. Now, for beyond GR, besides having the problem that we had before, we have another two, which is called trichomy and Kelvich, which I didn't know until Luis, right, or Franz and Luis in different papers, they wrote out those papers. It's because trichomy equation is a PDE who has different characteristics. So it's a transonic, it has a transonic line, and it can behave like a hyperbolic or elliptic. I always confuse Kelvich with elliptic. Means that it's an elliptic equation, like a boson one. What happened, and this is what my code was crashing, when you evolve this alternative field of gravity, especially Hordensky one, if you track the eigenvalues, the velocity of your system, they cross 0. Okay? And that is an elliptic radial forming. And this is problematic because you are evolving something hyperbolic who became a high elliptic, and then your code crash, of course, because your numerical methods are for a hyperbolic equation. And then we have something more problematic that I'm trying to find a solution, which is called Kelvich equations, which is this one has a divergence. And here there is another plot that basically say that the characteristic speed start growing, and then there is a condition that you violate, you cannot see. So if you want to simulate, especially Hordensky, you have to take care about these two regimes, let's say. They call instability now. So let's go to the scalar Gauss-Bonnet. So here is my summary about the scalar Gauss-Bonnet. So is that Lagrangian there. Here we have the Gauss-Bonnet invariant. Here we have a function, a coupling function, and a coupling constant. I will say, and there is a typo here, it should be, it's an approximation. At some point, I will say linear or quadratic Gauss-Bonnet. It means that I will change this function because all these people, basically, this paper here called scalarization, they have found many solutions for black hole or neutron star who has different characteristics. For example, compact objects like black hole or neutron star are no longer those of general relativity, so you can have black holes now that who has hair, or you can go under something called spontaneous scalarization, an instability who has, for example, you have a star, the matter pressure dominate and grow up this scalar field suddenly, and you have a not equal scalar field. So, yeah, depending on your F, you will have different solution for either black hole or neutron stars. And what we are trying to looking for, and this is something that I've been trying to do, is trying to see, since we are living in the gravitational wave era, I try to see if taking two of these and you collide, you can find something different, a smoking gun, okay? Because now we have LBK, LIGO, who was observing, which is observing many things, and I'm trying to see if there is any deviation. So far, no, but we will see. I will explain you why not yet. So, what happens if you want to simulate Gauss-Bonnet? And this is my, I don't know if you know this. Yeah, for people who play football. Because if you, I have a sticker with this, because every time that I'm collaborating, the code catch, and then I always send this because something always happens. I can tell you why. Do you know Marcelo Bielsa, no? The person who changed, yeah. And then we have Miguel Fernandez, the best players of South America. Even Argentina were saying that we were playing good. I say that in Argentina, it was a complete silence. And yeah, Marcelo always put Matias, and because he was very good, but always something happened, he breaks or something. And this is what I feel with simulations. Always something happened. For Gauss-Bonnet, you have an elliptic region. People call elliptic region. So depending on your coupling, this lambda that I show you in the beginning, if you start come up this coupling, you will form an elliptic region. And it's basically because all these Gauss-Bonnet terms, which are very nonlinear, all of this one, are entering the principal part and change all the equations. So if you take like very big values of this, the code will crash for these elliptic regions. And these people has done an amazing replay in France. Justin and France, they found this. So here is a summary about the progress of binary black holes. So since people, I don't know if at the time Helge and Thomas and all these people knew it about this, but then we knew that there was a problem. I mean, they knew it because I was working on this. They knew there was a problem about the well Poisson, okay? Because all of the equations of motion are very complicated and everything is coupled and things. They didn't have the Jacobian clearing. But the first approach, it was the coupling limit. Okay, so you evolve, so you have your if you take the equation of motions, you have the Einstein equation, the Einstein tensor, sorry, and the right hand side is all the Gauss-Bonnet terms plus everything. And then you have the box equation equal the Gauss-Bonnet. So the coupling limit means that you switch off all the right hand side of the Einstein equations. Okay, so you basically like evolve on top of something. And they did the first simulations, and they have the no hair and the hair and things like this. Then a friend, Aaron, he found a well-posed initial value formalism for this Gauss-Bonnet, which he called modified generalized harmonic. I will explain all of this name because I want to show you how well-posed later. What is all of this modified generalized harmonic? Just bear with me these names and then yeah, Aaron proved that there was a well-posed formulation. Then Justin and Will, they took this formalism, they could evolve, and they do more evolution. And then another friend in his thesis took another numerical relativity formalism and applied this idea. It's called the CCZ4, and now modified because it comes from the modified, and some people call them with punctual gauge condition. And then people were working a lot about this, trying to to do everything that you can do, because now you can do the simulation of black hole. So it's called modified generalized harmonic because he introduced new variables such that you can decouple the unphysical gauge to co-propagate. Then there is another two approach that I've been working a lot. I'm not going to speak about this, which is called fixing the equations. So this comes from relativity dissipative fluids, from a paper by Bob Genoch, who please take it the idea because Navier-Stokes equations are not well posed, but in a limit. So there are many things that you can do such that you can form like a well posed equations, which is basically, imagine that you have this equation very complicated, and here you have the problematic term. You promote the problematic term to a driver equation. And you have, at some time scale, you approach D1 to D1, and you find solution of this. Then there is something that is very active now, is the effective field theory approach, even though all of, before you can think about those one as an effective field theory, which is basically try to add terms to your Lagrangian with some constant here, such that try to cure the well-posted problems. And we have done something with Thomas about this, and now Pau, Aaron, they found another more general way to try to formulate all of this and try to do like, they are like really, they really prove that this is well posed, all of these terms here. But I will consider an alternative approach, which is recycling. Have to take care of where work, right? So I will try to find another formalisms. Let me explain you in one slide what are all the formalisms in numerical relativity. So if you remember, I explained something about strong hyperbolicity. So people try to put the Einstein equation in a strong hyperbolic form. And so here we have the generalized harmonics by Franz Pretorius. This guy this person was the first one who did a binary black hole collision of two black holes. He was the breakthrough of numerical relativity, basically, alone, competing against everyone. He did the first simulation. Then we have another very famous one called BSSM, come from Baumgarten and Shapiro, and Shibata and Nakamura, and another two Japanese kids that nobody put, I forget to put it. And they found out as well that they can formulate the Einstein equation, doing conformal decomposition of the equations in a strong hyperbolic form. And then something that I'm close is the set 4, which is it was the thesis of Carlos Palenzuela, my PhD advisor. So he developed a new formalism as well, tried to find a strong hyperbolic system to avoid the Einstein equation, promoting all promoting the Einstein equation, adding a 4 vector. For that reason, it's called set 4. It doesn't matter the name, but this is like the kind of history about all the formalism. If you do numerical relativity, you will touch all of this. Okay, they are better related than everything. Indeed, something historical that I like is that France discussed this problem about well possessed with another people who was working on that. And basically, he did the generalized harmonic, which is applied harmonic condition to the Einstein equation, which was the first paper in general relativity by Yvonne Choquet-Bruhat, who proved that the Einstein equations were well posed. So he basically took that idea and he did perform the first simulation. All the people were working on this one. Many codes were working on this. So if you see my previous slides, we have the modified generalized harmonic for Gauss-Bonnet, and we have the modified CCZ4 for Gauss-Bonnet as well. So my question, because I work with Aaron and Jiver, and I asked them, why didn't you do the modified BSSN? So you can complete all the formalisms. And they say, I cannot apply something. And I say, but you don't need to apply something. Why? Because I am close to him because I did the PhD with him, but they wrote 2 papers and people usually don't read so many papers. And then they have a paper who you can do transformation and you can go from this set 4 to something called set 3 and do a transformation and have the BSSN. So for a reason, classic never go outside. So what I did, I didn't give the idea to my PhD student, and we took Gibert, the modified CCZ4 paper. We go to the modified Z4, we went to the modified Z3, and we are right here. And these are the equations are very horrible, but we prove that they were well posed, and we complete the three. What happened? So now we have a new formalism, so we need to test. So the first test that we did in a scalar Gauss-Bonnet was a black hole with a spinning 0.7 plus linear coupling. And what you can see here, and we implemented this code from a friend. Have you ever heard about G.R. Chombo, maybe? No? It's a numerical relativity code from friends in the UK. Very good for doing black holes. And then, so what we did is comparing basically the two formalisms. Here you can see the scalar wave. So when when this black hole is rotating, with the rotation, with the spinning, you form a heavy black hole. The theory say that, and this is what you can see here, that the scalar field start from zero and have a profile, a non-trivial profile. And then what we did is we compare the errors, and we see what from our formalisms, the errors are bigger than this one. This is very well known in GR, but we want to see in beyond GR. So here the main take is that the scalar here develops dynamically and isolated spinning black hole, and we get the same for the one who was already the CZ4.
I have a question. So before you said that only for small lambdas in a scalar Gauss-Bonnet you could solve the equations, but now with these three methods you can solve it.
It's called everything because it's another 3 slide of it. It's called weakly coupling regime.
It's always still
Yes,
for small.
it's always. If you, to be more precise, if you want to crank up you need to go to this EFT approach or the fixing one. However, if you take small values, and people could say, but you are close to GR, I'm close, but I see phenomenology different from GR. I see heavy black holes. Usually every time that we put new formalism, we try to go up with the coupling, and they go down with scratch because the hyperbolicity problems. And then we did head-on measures of two black holes, and we calculate the gravitational wave for. So this is it's called the psi4, the 2-2 mode, the strong one of the psi4, and we see basically that they are the same. So now you should say, Miguel, they are not the same because there is a tiny difference, right? If you compare and agree with that, and this is usually what we see with different formalisms. So we are using different gauge conditions. So sometimes there are different phase. So what you can prove, and we didn't do that because it's very expensive, that if you take like very, very, very high resolution, the gravitational wave matches perfectly. But since we are not doing gravitational wave templates with that, we were super happy. So basically the two formalisms keep the same.
Miguel, sorry, I have a question about that. So before doing all this stuff, in my opinion, it's very expensive, doing all this computation. So first step, I guess you have to be sure that your solution provides some kind of static solution before evolving this dynamically or not.
Yeah.
Because
this is what we did before.
Okay.
So we found that. So the theory said that you have a stable black hole with here. We take one spinning black hole, and we get this is like this is the non-trivial scalar field that form the black hole.
Okay, but is
and
it
then,
possible?
sorry, this solution is analytic. You can even put analytic in the match.
Okay, but it's also possible that this scalar here exists in the dynamical regime, but not in the static one, or not?
You can form it. So you can start without something, without scalar here, and you can. Yeah, but this is called spontaneous scalarization.
Okay, but it should be coupled with battery.
Yeah. But it's always depend on if you are talking about black hole neutron star because
no black holes.
No, for black hole there is no coupling with matter. So I mean the scalar field, you mean? Yeah.
So, but in this case, first you have to be sure that the solution
exists and there are
inside.
Yeah, and they are stable under linear perturbation. And there are people who have done papers about linear perturbation on this. So I knew that they were so something I really like, and I love are neutron stars. So the question is, what about neutron stars? So what we did with this guy is a machine, Gibert. It's really a machine. He finished the PhD with 30 something papers. And he has a light, which is I was completely like shocked. I finished with 6 papers, I didn't have a light, but he was super happy. Okay, doesn't matter. He developed the GR Chombo code for all of these Gauss-Bonnet, and when I met him in a conference, I said, "Would you like to do neutron star?" He said, "Yeah, why not?" And we developed the new, in my code, we developed the code. Now we can evolve black holes and neutron stars for Gauss-Bonnet. It took us like 1 year and a lot of tears because many problems. So what we explore here is binary neutron star merger in Gauss-Bonnet, and we consider cases that you take 2 stars, they collide and they form a hypermassive. They don't collapse to a black hole. And there is another one which is called prompt collapse to black holes, which is you take stars which has like they are very massive, they collide, and basically at the second they form a black hole. I will show you the last one because it's the first one. The gravitational wave is the same from here, so which is something that we expect because they prove it. There was only 1 paper, so we have to check first, and yeah, we were happy because these people is very serious, so the code we find the same. So the first simulation that we did is a binary neutron star with linear Gauss-Bonnet, equal mass, and APR4 is the equation of state. So what you can see here is the gravitational wave. Basically is the Newman-Penrose scalar. The psi4, the 2-2 mode, the stronger one. This is the gravitational wave as a function of the time. A time equals 0 is when the 2 stars collide and form one object. So what the smoking gun that we found here, because you always try to find smoking gun with this kind of things, like try to do simulation and see if you find something new, was that if you take this scenario in general relativity, what you found, I mean, the star doesn't, the merger, the 2 stars doesn't collapse, and you have an hypermassive neutron star who develop quasi-periodical oscillations. And we start taking this value for the coupling, and we found that the stars after the merger, they really collapse. And if you count up the coupling, the prompt collapse is faster. So
what is the assumption about the scalar field in this case?
in which sense?
In like before you showed a single black hole, maybe you had an initial condition with 0 scalar that was agreeing, but here.
No, yes. So neutron star in linear Gauss-Bonnet, they don't have any hair. They are both. So
you have a 0 scalar.
Zero scalar field. So and this is what you can see here. So this is the plot of the scalar waves. Okay, all the scalar who is radiated at infinity. Again, time at merger, and yeah, they don't have any here. They don't develop. So this star behave like GR in the
Before the merger.
Yeah, before the
And
merger.
then after the merger?
They collapse and form a black hole. And the thing that we found that they form a hairy black hole because the scalar here in growth, and then you have a hairy black hole, which was fantastic. And then, okay, this plot created a lot of fights in the collaboration with my friends because I'm not a person who like to put 3D plots in the paper because people don't understand. Because if you don't do a simulation, you don't understand. And my other 3 collaborators fight against me and they say, let's put a paper. And then we have to change because the referee didn't understand the plot, of course. And then we sent the paper to different friends and they didn't understand the plot. But yeah, I couldn't change it. Let me try to see if I can explain this in a good way. So here we have quadratic Gauss-Bonnet, okay? I changed the function coupling, okay? And now the stars, they have hair. They go under something called spontaneous colorization. So they generate hair during the evolution. So here the different color codes. So here, this color here is the density of the star. This one is the scalar field, and this one is the apparent horizon. So where is all of this here? We will see. So now I'm showing to you 3 different different times: the latent spiral, the merger, and just after the merger. So here we have the stars here. They develop a scalar field, okay? And then they merge here, the parameter from 20 milliseconds to 21. and here is a zoom in of the merger. You have all the matter surrounded, and the scalar field start to reconfigure due to the strong curvature, and then we have the formation of a black hole here. This is the binary horizon, and we found this mushroom form, which is something that people found it before. So basically, what we found is something called a spin-induced scalarization. So the black hole is rotated so fast that the scalar field reconfigure at some point and form this heavy black hole with this form here. Yeah. So, for example, this was a paper from a friend. Nobody read that paper, and I knew that you have to find this form. But if you don't read that paper, you don't know that it's a matchable form. But basically, the main message is like after the prone collapse, you form due to the spinning, this black hole is scalarized. So you have a non-trivial configuration for the black hole.
But the neutron stars were not spinning initially.
No, this is the second paper. I'm in the 42 minutes. How long I have?
Got it.
People were starting. Okay, so now my enemy and friend cases. Yeah. Why? Because this was my postdoc for 3 years. And I suffered a lot with this one for 1 year. But then we are friends. Okay, let me try to explain. Have you ever heard about this? Because I heard before leaving this country, and I thought, okay, nobody will use this. People use quintessence or something like this, and then the generalization. But yeah, I never thought that I will encounter it in my life. So my takeaway of Callejas. So this is the action people use for cosmology. They try to explain the early or the late time cosmology. Late time cosmology. Some people use it for inflation. Some people use for the acceleration of the expansion of the universe. And there are very famous paper by Bukhanov and Babbage and so on and so forth. The good thing about this is this here. So after this event, where Maxwell has a very important paper, so people try to see which theory they can kill. They were waiting for something like this. I don't know, this is my feeling, but everyone was waiting for something. I will show you why, okay, because it's very funny. So what happened that this theory remained unconstrained by the bounds of the gravitational wave, the propagation of the gravitational wave. So what happened? That day in archive, 2 papers with the same name appears. I have never seen something like this. So as soon as we have this one, there were 2 papers with the same name. I think you check the name. And then for the phenomenological side, they have something called screening. Have you ever heard about screening mechanisms in scalar tensor theories or something like this? So let me try to explain. This one has kinetic screening, but basically imagine that you want to have a theory with a scalar field, and you want to pass the local test. But at the same time, you want to explain cosmology. You want to explain that the universe is accelerated with this scalar field. So you need to hide in some way the scalar field. Okay, there are different ways to hide this scalar field with a potential. This is called chameleon or symmetron. Then you have the kinetic one, and then you have the famous one, which was, I think, the first one, which was Weinstein, which is the second derivative. So people call this one camouflage. So they try to hide the gradient of the scalar field. So you have a screening radius, okay, here, and inside of the screening radius, you don't see anything different. You see GR. Okay, and outside of this screening radius, this theory in this case, they have the division of GR. So there are plenty of paper about this, but my main goal was what happened with this in the nonlinear regime. Okay, in the nonlinear regime, in my case, it will be neutron stars. So the model that I consider is the following. So the action again, I consider this model because you have a chi of x. Okay, and I take an effective field approach, you can say, but I take this cubic one. We come out with this model. You can find another one, but I will explain you why I take the cubic one. The important thing that for beta and lambda equals 0, you have Browns-Dicke. Okay, something whatever who doesn't have any screening, very constrained. And then if you want to your theory to explain that energy, you need that your cutoff, the strong coupling, sorry, of the effective field theory, this lambda here that you put, it has to be in these units that I don't like. Okay, but if I transform in units of my code, it's 10 to the minus 12. Okay, so look, to take that number and put it here. It's a very huge number. Okay, and I will explain you. And please, when I show you the plot, see the lambda. The lambda is the most important message because it's an open problem yet. So the equation of motion, you take the variation, whatever, you do this, but you have, so Einstein equation, the Einstein part, this is the matter part, this is their coupling. Okay, all of these look beautiful when you do everything, but you have a modified term here, like a modified Klein-Gordon equation. Okay, so because if this is 0, this is just the Klein-Gordon, but you have this term here, which is very annoying. Why is annoying? So you can recast all of this wave equation in an effective metric, okay? Give nu plus something else. But this something else, which is in red, can create a lot of problems, especially when you simulate. First of all, it can generate shocks, even if you take smooth solutions. So you form peaks like this, and the Cauchy problem, something I explained you before, it can break for all of the Kelvin-Gentry-Comey problem. So I'm not going to speak about shocks because it's something that you can, something new that we apply. So I work a lot with fluids. So what I did, I apply all the numerical scheme for fluids to the scalar field because fluids generate shocks by definition. And then the Cauchy problem that we found was model dependent. For that reason, the cubic model. The cubic model was a cure for the Cauchy problem, for the initial value problem. So just in a very nutshell, let me take the equation in spherical symmetry. If you calculate the principal part and then you take the eigenvalue, the hyperbolicity, and all the beautiful history that I told you before, you find that the eigenvalues or the characteristic speed are given by this. So we will say that the system is strongly hyperbolic if only if this is the definition are real and distinct, and you need to satisfy this condition. Okay, this is the most important one. Because if this is greater than 0, this became imaginary. You form an elliptic region, you have a trichomy. And this is what I explained here. So you can solve this problem with quiescence choosing your model. It's model dependent. And this, for that reason, we take the cubic. For the cubic, the determinant is always greater than 0, so I can do simulations. So I'm unsafe. There is another problem. It is a Kelvin problem. This is something I say in the beginning. I want to solve something, I don't know how to solve, but yeah.
When you say cubic, you mean that you only have x cubed or you have both x cubed and x squared?
You can have x squared as well, and you will get the same. Yeah. And then reading paper by your friend Claire, I didn't know that this expansion that I took is the nonlinear completion of the DVI model, the Dirac-Born-Infeld. So, but the thing that it was my second project doing simulation in Dirac-Born-Infeld because it's a very, very nice screen. It's fantastic. It's the most beautiful screen I've ever seen. However, these characteristic speeds are huge. You cannot simulate. So this is something I'm trying to solve, but I didn't have anything so far. So I will show you 3 cases, something called stellar oscillation, binary neutron stars, and mixed binary. So the idea of this simulation is test the screen, okay? So what I'm gonna do, I'm gonna show you simulation of this, and I will extract the smoking gun and the scalar tensor theory, which is the scalar waves, okay? So if you have a screening, this wave, it should be a screen at infinity. So this is the thing that we try to test the screen. Let me show you and see if you get the idea. So if you take time equals 0, polar coordinates, whatever your favorite metric, and you solve the TOV equations, you don't see anything. So this is the solution, for example, the pressure, the real pressure, the real profile of the pressure of the quiescence, so you don't see anything in the fluid. Where the beautiful things appear is in the kinetic screening in the derivative of the scalar field. So that is a schematic for the screening inside of this radius. you should have an screen scalar field, and outside you have the scalar force. And here is a plot about this. This is log scale to maximize the, because if you put in normal scale, you don't see. But Bronsike is a theory who doesn't have any screen. So you see something like this, just like this. However, when you take quiescence, which is the one that who has a screen, you see that this is the radius of the star. You have suppression of the scalar field compared to the Bronsike who doesn't have any scalar field. And yeah, we integrate until here the very long scalar field. So now I took the solution, okay? So a neutron star with a huge scalar field who was after a screening radius. Inside the screening radius, the scalar field you don't see was the arc, the solution, and I fit a code who can evolve neutron stars with quiescence, and I took a hammer and I hit the stars. So basically, I did perturbations of the stars. You can put a Gaussian whatever, so the stars start oscillate. This oscillation creates oscillation in the scalar field. It's called breathing mode, and the star oscillate. This scalar field start oscillate, and you can extract the smoking gun, which is the scalar wave signal, which is given by the Neumann-Penrose scalar 522, which is basically you can do the calculation and find that this is the second time derivative of the scalar field, aka monopole scalar radiation. So let's see here.
Miguel, is there any physical reason to fix the screen radius or not?
No, the screen. So when you don't. The screen radius is given by the theory. So you integrate and then you calculate.
Okay, but it depends on the fields or from initial condition or
No. It doesn't. You give an initial condition for the density when you do a TOV.
Yeah.
You integrate. You give your initial data. You integrate, and then there is a formula to calculate the screen rate. You just give it. The thing that you have to calculate in a point where it's a screen, but it is something that you can do. Yeah, it's not something that you like tune.
Okay, but
it's given in the solution.
Okay.
Yeah.
So not something arbitrary that you put at hand.
No. The only thing that you put is boundary condition at infinity. You say the scalar field decay 1/r, but you do the shooting and that's all. But when you get the screen radius, is really the physical solution. I didn't believe about this because the paper, when I saw it, I was like, oh, you can see this. You can see, because people try this solution. I mean, like solving the TOV for a particle, like a point particle. So I didn't believe that if you put a neutron star, and we have it. Okay, let me come back to the radiation, to the scalar wave radiation. So here you have different values of lambda. You remember lambda, this value very tiny. So I want to study quiescence in the dark energy regime. I could. We will see here. Why? Because that number was so tiny, so I could just arrive to 2 mega electron volts. And then if you remember the number, it was 2 to the times 10 to the minus 3 for being dark energy. But what we did to overcome this problem, it was I did plenty of simulations of this star with oscillations. I extract the scalar radiation, the monopole scalar radiation outside of the screening radius of infinity. And what you can see here is as soon as you decrease the value of lambda, decreasing the value of lambda means you have like your star more screen, the radiation is screen. So you have a big amplitude, and you ended up with something that is really screen. Okay, and then here we did a linear fit because I would like to simulate 10 to the minus 3, so it's like here. So what we found that the scalar field follow this linear one, so you can extrapolate to dark energy values, and basically the answer was like in this case the screening works for this case. Okay, doing this extrapolation. It was the only thing that I could do. Okay, I don't like to do extrapolation, but I have to do something. Then we take binaries. We did binary neutron stars. And then here, just focus in the red line and the black one. And this almost 1 hour. Okay, so here when you have a binary, you can emit the scalar wave radiation, not just it doesn't matter, this is the gravitational wave, so I want to test the scalar wave radiation if there is a screen or not. So you have the quadruple one and the dipole one, okay? What we found here that the screen is not effective. Why? If you compare from this simulation, this Brandzinski is a theory who doesn't have any screening, right? So is here is the red one, and then we extract for lambda 4 megaelectron volt, which is that the starware screen is below. Okay, so the signal it seems that is going in the right way. But however, when we want to test the quadruple wave, this is the strongest one. We found the positive things. Well, we found that during the spiral, the signal for Brandzinski was below to the screen one. It means that here there is no screening. Okay, so and what we found that for binary neutron stars, the screening is not super effective. So we found we were like, there is something. The simulation are expensive, so yeah, but but something that nice that we find as well that when you take the two stars and they collide and they form this hypermassive neutron star, only was a star, again the screen recover. So the red line, which is the screen one, which is the Brandzinski is on top of the screen one. So the screen here is working. So far that it's been a kind of open question. We have done some papers now. Then some people, Masaru and Dina, they wrote another paper. They took non-spherical stars, so like really non-spherical things with many perturbations, and they say if you want to find a really screen for the quadruple, which is the strongest one for the scalar wave, you have to extract your signal always. So the screen range has to be larger than the wavelength of the scalar wave, which sounds kind of obvious. So what we did again, we are trying to test this because the simulations. So imagine that when you put the stars, the screen ranges are huge. Okay, so you want to put, and you want that this screen radius doesn't touch another one, which is almost impossible. Okay, but for that reason, we were thinking that maybe here the screen didn't work very well or it's not effective, and then we did the last case. Here I just did the code. Ramiro did everything, which basically Ramiro and Aiden, they did an analytical and numerical model, and they do the same for a black hole and a neutron stars. And they try to test the screen again and test the screen again. So they found the same. So if you tell Brandzinski, there is no the scalar waves are bigger than the screen one. With this approach, Ramiro could Ramiro is the first author of the paper. Could arrive until 0.3, which I just arrived to 4. So going from 4 to 0.3 is a lot. And they see that the signal is screen. And then they found the following, and I almost finished. So this is the quadruple radiation. They found that they follow the trend. So here, the quadruple is always a screen. So if you want to do dark energy, it's gonna go to 0. So everything. But for the quadruple one, for the strongest one, they found not this perfect line log scale. It finds something flatter. And recently Ramiro did more simulation of this, and these are so for neutron stars, and it seems that it's go like this, but not perfectly like this one. So it's still an open question. And I put this slide for nothing because some people ask me about black holes always, why I didn't do black holes in quiescence. The one reason, if you do quiescence with black holes are a solution of the theory, so you will not see anything. They are protected by the no-hair theorem. So what you have to do is, not clear, but is adding a potential with a mass. Okay, the mass generate not a not trivial scalar wave, and then you have different solution for GR. Indeed, they went beyond because they did qubit Galileos and I forget the name of that one. And so finally, my conclusions, and I finish. So yeah, I hope I convince you that alternative theory of gravity offer like a very rich phenomenology, especially if you combine with numerical relativity. Well, post-hyperbolicity is the key task to do simulations. You have to study no matter what. Yeah, and this is the first thing that when somebody come to me, Miguel, I want to do this black hole simulation. I'm very open. I'm like the soldier of numerical relativity. I simulate everything. But this is the first thing I ask. Can you prove that it's well posed or strong hyperbolic? Something nice that we are living in this new era of we are capturing more data for every Now LISA is coming, the instant telescope. We can test the strong field regime. We need more ideas. Maybe you are theoretical, I don't know, but we need people. So, for example, Aaron, the person who did the formalism, he's very theoretical and he's working now on this. We need people who even they do the math part, the equations, and then we discuss about strong hyperbolicity or PDE, and then we need people. We need new formulation, new ideas. And for example, always goes back to the basics. For doing this simulation that I showed you, I always read papers from the 90s where people, all the code were crashing because they were like trying an error. And this is more or less the same. However, now we have something like the codes and everything are working. So I hope to convince you that we can do simulations. There is the fixed integration program. So for example, people in Max Planck, they are doing a template with that formalism, with the fixing equation of black hole in a scalar Gauss-Bonnet, and then the EFT approach, which is very fun and very beautiful. And yeah, I'm trying to go to the EFT one, but I don't close the door to it. And then yeah, this is something all that I have that I keep this. I mean, I have this conclusion for the last year. I changed everything, but this I have from the last year, which I say maybe we are soon the NR beyond GR breakthrough of numerical relativity, as France did in the 2005. But I think this is not true. So we already passed the breakthrough of doing simulation of numerical relativity beyond GR because we have different codes. I show my code, the code of a friend, but there are other people who are doing this, and we really are testing. I mean, the hope of this is to test GR with a template of beyond GR. And maybe that template will say, look, GR is a theory. Stop Gauss-Bonnet, stop Kayerson, but it's science. And then, yeah, but not least, so I did my PhD in boson star in exotic compact objects and numerical relativities. So I was presented to the community exotic compact objects, to the numerical relativity people. They do black holes and everything, and nobody cares about my boson stars. So I was very depressive, and I found this quote from T.D. Lee of particle physics, very famous one, who say, at the present, there is no experimental evidence that boson stars exist. However, nevertheless, it seems reasonable that solution of well-tested theory, such as Einstein GR, the Dirac equation, the Klein-Gordon, they should find the proper place in nature. And for me, that was fantastic. And I was crying, I'm very dramatic. However, I did my quote, and I got alternative boson star and alternative theory. That's all. Thank you.
Thank you, Miguel, for your very nice talk. You have time for a couple of questions, maybe one or two.
I have a question about the templates. You said that they were making a template with this scalar Gauss-Bonnet. Now, suppose, so my question is this one. Are you checking whether Einstein gravity might need the scalar Gauss-Bonnet, or are you checking whether Einstein theory might not be correct? So, do we have the tools to make, for example, numerical experiments or whatever, that would enable us to check to see whether the Einstein theory is correct or not, independently of having templates of all these modified theories? Maybe they're all wrong. But maybe Einstein theory needs a correction, but it's none of the ones that you can build templates from. And you see my question is...
No, I agree with your last statement. So in my case, what I'm doing now, since I have the tool, and we were recording, I was about to say that joke, but I think those one is Storm's fault. Thomas Utili.
I see.
Yeah, but this is a joke. But in my case, I really want to. So you can correct me, Maca, because you work more in desktop GR than me. The null hypothesis, no? So they compare GR with GR for me. So I really want to do a template, and now we can. One thing that I've been trying to. So because people always say, well, especially because I showed the first slide that we have a zoo of alternative gravity, that there are many, but there are not many that we can simulate. So for example, for Gauss-Bonnet, you can take this value of lambda, and there is no match because then the code crash for hyperbolic. But you can have different deviation from GR. So my goal is do a template of this because now we have the GPU code, so I want to do like really a lot of simulation. And I'm working with, I mean, my group, there are people from LIGO who do data analysis. They have the tools. If I keep the gravitational waves and try to do what they do, the I don't know, the mismatch of the waveform with my point. This is my goal. But I answer your question.
I have another question, very quick. You said at the end that you need new ideas. In the old days, people doing computational or gravitational numerics, they always say we need more power, computational power.
Yeah.
So it's not an issue anymore. Now you
No.
more ideas or
No, because now the codes are very mature. As I say, the numerical method that we use, they are very standard. So there are some people, or and because I try to interact with math applied people in where I work, try to look, do you have any different? Because I use final difference. So what is final difference? Not so easy, or shock capturing method. But even if you change your numerical methods, basically the solution is going to be the same. The real difference now is GPUs. It's something that when I was doing my postdoc, we applied for computational time, and I was getting a lot of email from the different HPC facilities saying, we have a training thing for moving your code to GPUs. And a lot of this, and then we did it took like 3 years to move all the CPU code to GPU, and now we can do simulation like really, really fast. And so there's a caveat with GPU that I didn't know. I knew it for some meetings about HPC things, that everything is capitalism. So they are doing GPUs for AI, and AI, they don't need double precision. And I need double precision for maximum. I need very accurate solutions, let's say. There are a lot of numbers. So the GPU now, the one that want to be just for simple precisions. So all the effort that we import in the code to GPU, maybe in some years it's not going to work. But GPU now is like so all the numerical relativity community port the code to. There are a few codes that they are not porting, but it was the GPU. Last year we have the numerical relativity meeting with all the people, and then the GPU was like the big thing of the code part. And yes, we will see what happened with the single and double precision.
More questions?
I have maybe a root question of the day. When you start speaking about sterilization of black holes, there's a paper of Hector Silva, Tomás Otilio, and company, which calls explicitly spontaneous sterilization of black holes and compact stars from a Gauss-Bonnet coupling. And in that paper, they show the narrow bands where black holes sterilized black hole exists, and they compute the numerical integration of the decoupled scalar field from the center. So I can figure out what's the need. You show something new, or you just review that topic?
That paper is, there is no numerical simulations. There is no time evolution. They solve the static problem.
Yeah, the short shape black hole.
Yeah. But this is you are solving the evolution equation, which are the Einstein equations, coupled with all of this.
Mm-hmm.
So the difference is that this is a time equals 0.
Mm-hmm.
That paper, this is a time greater than 0. So we show all the evolution. And the thing it was, I mean, the new thing it was exactly the gravitational wave.
What kind of black hole?
Hmm?
What kind of black
The kind of black hole is what the Hairy black hole that you say. It was linear Gauss-Bonnet. I don't know. I don't remember the copy of the paper by Hector, but it was linear,
Yeah.
and quadratic, or just linear.
I think it's
Quadratic. So quadratic
goes
goes
to a scalar.
to the, yeah, because that goes out the spontaneous clarification. Yeah. Yeah. But this is calculate just solving the ODE. Okay, so you take many approximations, you take a geometry and everything, and you solve numerically an ODE. This is like I take that solution and I feed the Einstein equation coupled with all of this, and I let it evolve and I collapse this oil. I don't know if I answered your question.
Yes.
Yes, thank you, Miguel, again. Ahorita hay un coffee break.
Sí, la última cosa, yo siempre motivo. Si alguien quiere hacer simulaciones o está interesado en Numerical Relativity, acérquese a hablar conmigo, no hay problema. ¿Okay? Necesitamos gente, estudiantes motivados, latinos, americanos, resilientes.
Está hablando de eso.
Me leí se lo mandé a mi amigo para ver si se puede estudiar la...
No sé qué era una cosa.